I think I forgot to. There we go. So, as I was mentioning, for this last class, we are going to be talking about high performance R, and we have a variety of topics. This is by no means a complete list of topics that one would like to include when discussing high performance features in R. But this is at least a good number of them for starting. So we're going to be talking about memory management, we're going to be talking about profiling, launching parallel processes, and interfacing with compiled code, which is something that we haven't seen at all in the course because this is a course mostly about R. But it's something, it's a nice tool to have, and a few more things that are here and there during the presentation. Okay, as usual, if you have any questions during the presentation, please let me know. Let me know. I haven't heard anything from you guys, but let me know. I think my audio and I know the screen is being captured, but let me know if you can hear me okay or not. Okay, you should be hearing me by now. So just as a reminder, right, we know that R is an interpreted language, and what that means, we discussed this in the very first week of the course. What this means is that there is an additional layer of infrastructure, which is what we call the interpreter, that basically is waiting for our commands to be typed in, and then interprets these commands and execute. And this makes the language slow because exactly this, and because all the things, all the nice features that we discussed about are like dynamical typing, where you can basically change the type of a given variable on the fly. So all these kind of nice and useful things that are offered makes the language slow per se, because basically it's awaiting, or is waiting for the interpreter to handle all these things, all these features that we can change. So this is a common pattern with any interpreted language. R is one of them, Python, Bash, Perl, any language that has these features basically suffers from this slowness of the interpreter. The real high performance languages, the real languages that you will get the better performing programs, are written in compiled languages. And examples of these are C, C++, Fortran, CUDA for CPUs. And of course, the disadvantage is they don't give you as much flexibility or much nice features as interpreted languages, but the reason for that, there is a reason for that. The reason is that they can execute way faster. So that's the trade-off relationship, if you wish. Now, having said that, there are ways to make R not quite so bad, and this is what we're going to be discussing today. Now, there will be some caveats, right? And again, if you're going to just compare R versus a pure plain C++ code, this is more like, in a box match, put in a lightweight boxer and a heavyweight one, right? The comparison will be really, really unfair, but it's something to bear in mind. Now, one thing I should warn you is the memory consumption in R. And if you had to deal with big data, that's something that you probably had noticed. R is a very heavy consumer of memory, so it uses a lot of memory. And then that can be a problem if you are limited by memory. If your computation is what we call memory bound, which means it requires a lot of memory, then that's something to be careful with. Now, one thing that we didn't discuss much is how R manipulates the arguments that go into the functions. And the truth is that there is no real way in which, or there is no unique way in which R handles this. Actually, R tries to manipulate this by doing two things: by seeing if the function inside has to change the variables, then creates a copy, and that can be a problem again if you hit memory limits, right? So the good news is that many interpreted languages or dynamic languages like R and Python, they have something called garbage collection. And garbage collection is a program, it's another program that R runs, and every so often it goes and say, oh, are you using this variable? If you are not using this variable, then I will take it away. And this happens with variables that lives inside a code block, right? So it won't kill any variables that you are using. That basically is variables that you have used before that are kind of temporary variables, and then you can basically be safe that this will go away. Now, this is like they have an extra layer of protection to be sure that doesn't delete any variables that you need, but it can be faulty when you have variables that are hanging there, you are not going to use, and the garbage collector mechanism doesn't collect them, doesn't pick it up. It's very unlikely because garbage collection theory, believe it or not, there is in computer science, there is something called garbage collection theory. Is very reliable. It has been around for a long time. Languages like Java also use that. So it's quite reliable. Okay. Having said that, what I want to show you is how you can manipulate by hand this kind of Pershing mechanism, if you wish. So with that in mind and with the memory management in mind, we're going to see a couple of commands. Some of them we already saw, but now in the context of the memory manipulation or the memory management of the computer. So GC stands for garbage collection, and you can use it with verbose equal true or just GC true. And basically this won't help much, but it gives you a verbose output of what is in memory and what can be purged. ls, we saw this command, it basically lists all existing variables and functions defined by the user in the current state of the memory. Object size of a given variable name basically returns the size of that variable name. Now RM, and I think someone asked this on the very first week of class or something, basically allow you to delete a particular variable or function definition that is no longer needed. So for instance, this is what we call one-liner. It's a one line of commands, and basically what this will do is, and it will use a couple of functions that we have seen before, is applied, sort, you probably use that in assignment 3 or 4, I can't remember now. And this is what we call an inline function definition. So that function is defined there, is used there, but it doesn't have a name assigned to it because it's just used there. I think we saw this one in when I show you the apply family functions. I told you it's not my favorite thing to do, but in this case, if you are going to just use it once, it's a nice handy way and short way to declare a function and use it and then forget about it, right? So in this case, what is happening here, the sapply is going to be applied to all the elements returned by ls, the list of variables currently present in memory, and it's going to apply this function. And what it's going to do is it's going to obtain the size of the element, so each of the size of the variables defined, and it's going to order it in decreasing order. So first the largest and then the smallest ones. So if you use, so let's say I have in this case a few, this is a session, an R session, where I have declared some variables there. So if I do GC for garbage collector, it will tell me N cells and B cells. So N cells refers to memory associated to variables that can, like scalar variables, all kind of variables. B cells refers to the ones that are vectorizable. Okay, so don't worry much about that. It's just a way to differentiate the type of variables for R. And you can see here the sizes in megabytes, and then when the garbage collector is going to be triggered, and what is the maximum use. Okay, so let's say I want to store this information, so I'm going to call a variable getMem, and then just for not real good reason, I'm going to define a function, but I could just have assigned this. Okay, but this is a function definition, again a one-liner function definition, which basically calls the garbage collector and it stores only the first two columns, right? Comma 1, 2. So this is a data frame. 1, 2 basically stores this, which is the actual information of the use space in memory. The others are more like statistical indicators of how the garbage collector will work. Now I get this this information. That is my function basically. So I can call all mem and basically get mem, and then I'm going to create a vector full of zeros with a very large number, so almost 16 million of zeros. I'm going to obtain the size of that. Basically, that gives me the size in bytes, which is useful because it's already a kind of unit in the size of the object. But one of the nice things is if you use the print function, you can specify the units and say, okay, give me that in megabytes or gigabytes. And then it gives you, okay, this is 2048 megabytes, almost 2 gigabytes. Okay. Now, if I use my get memory information, my get memory function I define here, and I get the new mem, now I have the old mem before I created the vector x, and the new mem after creating the vector x, so I can subtract these two. And if I subtract these two, because my function only keeps these two columns, then I get that basically I only get 2 gigabytes more in the B cells. Okay, this is something tiny, it's kind of garbage if you want or no. It's something that probably R is storing the history of your commands or something meaningless, right? But basically what you see here is the difference in megabytes of the creation of the vector x. Okay, so this is a kind of a handy trick to keep basically a track of how the memory footprint is being used in the computer by creating options. Okay, now let's see if our friend RM, the remove object, works. So now let's try to delete the object, delete RM, so RMX, and now the final memory is again our function get memory, and then what I do is final memory minus all mem. Okay, and basically that gives you CU again. As I say, these end cells maybe not exactly zero because there are some things that are needs to keep track. It's usually called function call stack, which basically is, if you remember the history command that leads you the list of functions that you're calling, is kind of related to that, and other internal indicators that are uses for its own session and its own management of the session. Okay, so we saw a couple of useful commands to get an idea of how much memory our objects, our variables may be using in memory. Okay, any questions about this? So the bottom line here is, whenever you have these huge arrays or matrices or something that are temporary in your functions, you can basically wait for the garbage collector to delete them. But if you are certain, especially if it is something really large, if you are certain that you are not going to use it, just add a rm call there that will basically prune and release the amount of memory right away. And again, I want to emphasize that R is well known for having this compulsive behavior of keeping things in memory until the garbage collector kicks in, right? And that in some cases it can be a little bit conservative and take longer to basically do that pruning for you. So any questions about that? That's the part I want to mention about memory. There is for certain way much more than one can say about memory, but I want to cover a few more topics, so that's why I'm going to stop there related to memory management. But again, if you have any questions, please do let me know. Okay, we're going to talk about a very interesting topic now. We're going to talk about a very interesting topic now, which is profiling. And profiling is a systematic way of measuring, of basically analyzing how your code performs, but also trying to find where it takes or where it spends most of the time. Okay. So basically, let's say we have a code and we have a couple of scripts and a couple of functions, and we want to know which part of the code is the most expensive for the computer, is the one that takes the longest. Now, I had to tell you, profiling is done not only in R, but in any language, even at the level of the operating system, and not only in regard of time. In this case, we are taking time as a metric, as a variable that we can measure, but we can profile also memory. We can say, okay, how much memory a particular function is using. In this case, we are going to just focus here in profiling time, in profiling how long a particular part of the code takes to run. So we have different tools that we're going to see. One is called micro benchmark, which is a package, and I think you need to install it. And then system time, that is a tool that is already part of R and is basically provided by the operating system. And what it gives you is an overall view of the time. So one allows you to take a very detailed look at what the inside of the function is doing in regards of time, and the other give you a more crude raw view of the overall performance of the code. And in addition to that, we're going to see another package called rprof that is for R profiling, and basically it profiles your whole code. And we're going to see examples of this in the next slide. So let's profile individual functions. I have a function here called f, which basically assigns a value and then iterates for a very long number of iterations and add just one to that, add that number to the variable a. Okay. So the first thing I'm going to show you is the system.time function. This is an R function that basically uses the time command from the operating system. So every operating system has a time command that basically measures things. So directly I can do system.time and call my function. This function doesn't have any argument, but you decide to do whatever you want. A function with multiple arguments, you will call the function as who you will call it usually, and then goes and measures the time. Now when it measures the time, it gives you three different columns. One is the user time, the system time, and the lapse time. So the lapse time is the total time that the function took to run. Basically it's the addition of the user and the system time. The user time in principle is the actual time that the function runs, so it's the time that you as a user spend. The problem with that is that if your function is doing some input-output, like printing something on the screen or saving something to a file, that is considered system time, even when it has to access information in the memory. So that's why we always need to look at the lapse time, the total time of the function. So for the system, you can differentiate between what the user is doing with the function and the request to the operating system. And that is what the system call, or the system time, refers to. But the truth is, this function took 1.789, I think, milliseconds in run. Now I told you about the micro benchmark library or package. So we call that micro benchmark, and we can do exactly the same. So instead of using system time, we will do micro benchmark the function. What is the difference with this one? Well, it gives you a little bit more of information. As you can see, the time doesn't change much. But the nice thing of micro benchmark is that it runs many times. So it runs, I think, by default 100 times the function, and then take the average of that. And that is a more reliable result than just running once, because in some cases, let's say that, like for instance, now if I run this in my computer is trying to record the video, stream the video, capture things, do the video conference. So it's very busy, right? So if I run my function now while my computer is busy, this time probably is going to be longer, and I will be able to see that maybe in the system or something else, but this is not a reliable measurement of my function per se, but the overall load of the system. So when you do micro benchmark, what it tries to do is try to mitigate fluctuations in the time that you were running the function, and that's why it runs the function 100 times and then take the average and give you the minimum, the mean, and the maximum. Okay, so it's always a good idea to take a look at the mean, for instance. Okay, it also tell you the units, so that was seconds, so that's seconds. Okay, so two useful functions: system.time, which comes with R, and then from the library micro benchmark, the micro benchmark function. Okay, very easy to use, right? After you have your function definition, why not testing the function and see how long it takes to run, especially if it is a really heavy function in the sense that it takes a long time. Now I have another example here where I'm going to use to show you how to use rprof. So in this case, this function is called admin. Very simple function actually. Takes two arguments, a and b, and then returns the addition, the sum of these two variables, and it can be vectors, can be numbers, whatever you want. Then I have another function called test, and basically this is similar to the previous function. The only difference is that instead of using the addition directly, it used the admin function. Okay, and the reason for doing that is kind of silly, right? I could say a equal a plus I. It's just to show you how rprof will distinguish the codes to these two functions. So the way it works is you do rprof, and then you say where you want to save the data. So this basically will start profiling anything you run here, right? So you start with rprof, and then the name where you save the data. You call your function, in this case the function test. This function will be executed, and then you finish the profiling with rprof and null. Okay, so whatever goes between rprof and the name of a file and then rprof null is what you will profile. And then what you do is you do summary rprof. That's another command from the rprof function, and you bring back your data, and you will have all the information of what you profile between the rprof and the rprof null. In this case, I'm assigning this to a variable s for summary, and then s has a lot of different things. You are more than welcome to take a peek at that, but the one that is interesting usually is by total. So if you do s $sum by total, as you can see, this is sort of a list. It will give you a data frame which contains the name of the functions that were used, the total time, and the self time, and the self time in percentage. So this is the total time in percentage, self time in percentage. So in this case, the test function took 100% of the time, because obviously it was the only function being called at the main level. But within the test function, we had the ADME function, and the ADME function took 41%, almost 42%, right? This anonymous is related to basically the timing that R uses and other things that R does, right? All this internal handling of the data. But basically, you have here a very nice overview of how functions that call other functions behave, and which function is using most of the time. Right? In this case, clearly the test function, because it has this looping, and then it's calling this ADME function, which adds to that, but it's nothing else than just an addition, so it's not so bad, right? But this is, again, it's an example of how you will use rprof to profile multiple calls and multiple functions at the same time. Okay, so we saw system time, we saw the micro benchmark utility, and now rprof. So 3 tools that you can use for profiling, for measuring how your code performs. Okay, the reason for doing that, I don't think I mentioned this, but the reason for doing that is, well, for once, we want to know, we want to understand where most of the time in our computations go. But the other reason is, if we understand where the code is spending most of the time, then we may be able to optimize that. And that is what we're going to see in the second part of the lecture is, okay, if I know this function or this script is spending most of the time calling this function, then I should spend most of my time trying to optimize that function. I think I saw a question. Let's see. So Richard, if you were to run this code again, could rprof override? Yes, if I use rprof data. Okay, I think there may be a flag to say append equal true, but by default I think it's going to override. So it won't affect the summary unintentionally, but it will lose whatever you had before. Yeah, good question. So some notes about rprof. So rprof, this is important because this has to deal also with the way that we do the profiling, and there are 2 main techniques for that. One is called tracing. I didn't include this in the slides because it's not so relevant for the lecture today, and the other is called sampling. When you do tracing, basically you follow every single call of the program, and that's a very basic way to do a profiling, and it's doable, and there are tools for doing that. But in this case, rprof is doing what is called sampling, and it's like a statistical sampling actually. So what happens is every certain time, in this case 20 milliseconds, goes and check which part of the code is being executed, and basically goes and saves that. Okay. So rprof, as we saw, file name stores the results in a particular file, and this turn it off. The file, I believe, is text, so you can basically go and look at it, but summary rprof basically aggregates the information for you in a nicer manner. I think I mentioned most of the things. Total time and total PCT include the time spent within a function and calls to other functions. Self time and self PCT indicates actually real time spent in each function. Okay, and as we saw, it should be for the main function 100%. Okay, given or take roundings, of course. Now, as I mentioned, previous part was about measuring and understanding where our calls, our functions spend most of the time. What we are going to see in the second part of the lecture is how we can mitigate that. And as I mentioned before, codes or programs can be limited by different factors. It can be limited by memory because they use a lot of memory. They can be limited by speed, which means, okay, I had to run this code and it will take 1 week. That's nothing. I can tell you one of my simulations may take months, like 3 months in run, and they cannot run all together all at once, so I had to do checkpoints. I think we talked about that some time ago. But in any case, in that case, the computation is limited by time and in some way by speed. So these packages, what allow you is to help these two problems when a computation is limited by the resources, the hardware resources that you have, or the time that it takes. The first package that we're going to take a look at is called the parallel package. The parallel package has been around for more than 10 years now, or at least 10 years, and as part of the core R, incorporates many other packages, at least 2 of them. One is called multi-core, and this is when you want to use many cores or multiple cores on a single processor. What this means is nowadays, computers has many cores, many processors inside the same computer. Think about even your cell phones nowadays has multiple cores, and what this allows is to spread any computation within these processors. Okay, this package was to use multi-core. I just include this because you may see some programs still using that, some R scripts still using that. The other was called SNOW, which stands for Single Network of Workstations. And this is when you have different computers and you want to distribute your computation across different computers. And of course, you need a way to communicate with those computers, and that is the network. Okay, so in this case, you create new processes and you distribute these processes, and you need to send information, also the data that those processes need to run in the different computers. In the previous one, these communications happen through messages, but also through memory. Okay, so one caveat of this is doesn't work on Windows because the operating system on Windows doesn't allow you to do that, but in Linux and macOS you can use that. Okay, now there are many other packages, and I have a link at the end in a nice web page, a nice resource that summarizes different approaches to this depending on what the problem that you are trying to solve is. Okay, the one important thing to differentiate here is what we call processes and tasks. So a process is something that is independent and it doesn't have the same information in other processes, so we need to send that information. And a task is something that shares that information and it doesn't need as much information. It doesn't need as much communication in the sense that you need to send the information for doing the computation. These are very, very subtle points, and it will be more clear as we go into the details of the packages, but I just wanted to give you the 2 big pictures here regarding parallel computing, and we are getting into the world of parallel computing, by the way. So let's start by looking at NC parallel. We are going to I'm going to show you an example. I will recommend you run this example after class, because in some cases it may take some time. We are going to first of all load the library parallel, and the other thing I'm going to do is I'm going to load some data. Okay, and this is air traffic data from I think 1998, the month of June, just the month of June. It's a long data set because it's from one of the airports in the States, or the whole airports. I think it's all the airports in the States. I can't remember exactly, but it's a long data set. So it may take some time to load it, but even more time to process it. So one of the things I want to do is I want to know the unique planes ID, and for doing that, in the data set, which I call Shun 1998, there is a field, a column called tail number, which is basically like a ID plaque of the plane. Okay, so what I want to do is I will do unique. I'm going to sort it as well. That will increase a little bit the time. I could just use unique, and then I'm going to get the length of this. Okay, and you will execute this as usual in your computer, but as I said, this is a long data set. So instead of doing that, what I'm going to do is I'm going to use MC parallel. Okay, so MC parallel, what it's going to do is, this is the MC stands for multi-core. So what this is going to do is it's going to distribute the task of sorting and looking at the unique ID of the planes between all the processors that you have in your computer. Okay, and then I want to compute, for instance, the median of the elapsed times of the flights. Okay, and so I'm going to compute the median of the actual time, elapsed time of the flights, and then remove any NAs if there are. Okay, and again, I'm going to do NC parallel of that. Usually we'll do median, and that's it. And I'm going to place this in unique planes and median elapsed. Okay, now what happened here is, if you look at these things, there's nothing there, because these are just instructions for the MC parallel library to go and execute that in a parallel manner. So it may happen that when you go and type your second line, the first command is still being executed in the other processors. So for getting your results, what we need to use is MC collect, so multi-core collect the information. So what this will do is it will go and ask each of the processors that were involved in the computation and say, okay, remember I asked you to compute unique planes and median elapsed, can you give me back those results? And then I put them together for the user. And that's exactly what MC collect does. Now, as you can see, you can specify many functions or many variables that were defined in this way. And basically, when you look at the answer, it gives you a list with the different results. Okay. Now, the list, as you can see here, is named with a number. Okay. That number is the process ID that, when you ask the computer to run that particular task, give to that process. So every time that you ask the computer to do something, identifies that as a process ID, a number associated to the process. And that's the process, the ID of the process that was in charge of finding how many unique planes were, and this is the median, in this case, of the actual elapsed times of the flights. Okay, so it's very easy to use. The only thing that you need to really do is MC parallel for the operations you want to do, and then MC collect. Very straightforward. Just by doing that, R and all the infrastructure within is able to distribute the computation in the multiple cores that you have within your computer. And I want to emphasize that this is in the same computer. So if you have a computer with 40 cores, then it can distribute within the 40 cores. If you have a computer with 8 cores, we'll use 8 cores. Okay? See if you have a question. I don't think so. I think it requires to be explicit about this, and the reason is maybe in some cases, maybe it's a good question, Shinji. Maybe in some cases you expect to have one of the NC parallels taking longer time. So I don't think by default it's going to do that. I should double check the documentation, especially because this is a known library and it may have changed the approach. But as far as I remember, it doesn't do that. So you need to be explicit about all the functions you want to collect at that time. There are other subtleties, but I don't think is not going to do that. That's called race conditions. So let's say that this quantity has to be computed first, and this one depends on this. So if you start the computation, if you collect before this one is done, you may run into this sort of race condition. It's a new type of bug that may crawl into our programs, but that happens because we are moving into the parallel world, the programming of parallel computers or parallel approaches. Okay, but that's why I don't think NC collect by default will collect the things. I may be mistaken about this, especially because they may change the default, but I don't think that's the case. Okay, good question. So let's try something else, and let's try now to compare, because I show you how to do it, but let's say, okay, is this useful at the end? Is something that we can use, if we can take advantage of this. So let's say that we want to run a feed, okay, and now we're going to feed, for instance, distance versus airtime, so how long the flights flew, and how long it took. So, and then we're going to feed, for instance, arrival delay versus departure delay. So two things that may be correlated or not, but this just, again, is an example to see. And what we're going to do is we're going to do a feed 1, which is distance versus airtime, and feed 2, which is arrival delay versus departure delay. So what's the flight delay when it arrives is related to the delay when it departs. And in average, what you will see, so remember our user system time, we're just using system time here for simplicity. We could use micro benchmark if you wish, or rprof, but for simplicity, let's say it took 0.275 seconds the first feed, and 187 seconds the second feed. So in average, so adding these two, both feeds took 0.46 seconds. Again, not crazy times, but again, enough data to make it crunch a little bit. So let's see, in this case, how we will do this with MC parallel and MC collect. So I'm going to call this part feeds. It's a function that depends on a data set. The data set is the data that we just read. And so the first feed, the first parallel feed, is going to be MC parallel LM. So same thing as before, the only thing we decorate things with MC parallel. And finally, we call the MC collect with the list of the feeds, the parallel feed 1 and the parallel feed 2. Okay? And then what we are going to do is system time of our parallel feeds function that we just defined, and we pass the data, okay, that we want to use. If we do this, we see that now our total time is 0.65 seconds versus the 0.46 second that we saw before. So now you may ask, okay, why is this? Are we spending more time? And you know what? The truth is, yes, we are indeed spending more time. And the reason is we don't have enough data to keep all the processors running and using advantage of the parallel computation. So what happened here is that when we have parallel computations, we basically need to do more work splitting the data and sending information to each of the cores. This is called forking the processes, and then waiting for them to rejoin and combine the data. So all this is called overhead. When you need to do this administrative work to split the data, send to the processors, instruct each of the processors what to do, and then collect back the data, bring the results together, this is called overhead. And the process itself is the forking of the processes. So what happened here is when we divide the jobs, when we divide the tasks, and we combine them again, it's taking some extra time that is making the difference for this. This is a signature, this is a sign that what will happen here is we don't have enough work for the processors to make, and we don't have enough data that is worth exploring the parallel division. So in other words, we need to provide more data, give more data to these processors, and then the overhead is going to be basically meaningless or a minimal amount compared to the actual amount of time that the processors are doing the work. So this is a kind of a corollary of the parallel programming. You need to be sure that you have enough data to keep your processors well fed and busy enough so it's worth spending the time in the division of the data. Okay? Again, this is an example of how you will do the MC parallel division, but also to be aware of not overkilling the problem if you don't have enough data, right? This is a technique that is very useful and very powerful when you really have a lot of data and when your computations are taking a lot of time because your only core where it is being run is overwhelmed with them. Okay? All right. So another way to for this is to use MCL apply. And this may ring a bell because we basically are calling our old friend lapply, but by using the MC, we are forking, we are dividing the process across the cores. How we will do that? Okay, another simple function, add me, a function receives one argument, and then add, it does just a mathematical manipulation, it adds n times a value by doing some mathematical computation. Nothing completely meaningful here, just a waste, a means to waste time and do some computation based on the number n. So we're going to do our comparison with system time. In this case, I'm going to put the results in the list of results, and I'm going to do MC apply, and a repetition of in this case is what is that, 10 millions 4 times. I'm going to call addme, the function, and this is a new parameter that we see in MCL apply, mc.cores, how many cores I want to use. If you don't do it by default, it will try to use all the cores, and this is a way to control how many cores you want the MC apply function to use. Okay, so in this case, when I do that and I do my system time, so basically this is calling the function addme 4 times and with 10 million each time. So it will do this 10 million. So it will be like 40 million times the execution of this addition or division, whatever it is. That gave me a total time of 2.40 for 2.5 seconds, let's say. If I do this using just lapply, which is, remember, lapply is one of the really good functions that are provided because it's optimized and it's vectorized and it has all the goodies that we want. And I just do the repetition of the 10,000 times, 4 times, calling the addme function. Now we see that it almost takes 4 times the time that it took with MC apply, because MC apply was using 4 cores. So basically, this is pretty close to what we call perfect scaling. I took a problem that basically took 10 seconds. Let me simplify this in terms of the numbers. It took 10 seconds, 9.5 seconds. I divide the problem in 4 processors, and the total time is basically the total time of the problem divided by 4. So this is one of the best case scenarios that you can have when you do parallel computing. You take a problem that runs basically, let's say, serially in only one processor, and you divide in n, and then your total time is divided approximately by n. So this is a very nice example, and again, it's a very simple use of MC apply where you just call almost the lapply function, but you can one additional argument where you specify how many cores you want to use. Okay, so very, very highly recommended, I would say. One final note is if you take a look at the processes, and this case was my good friend Eric Spence running this. If you take a look at the processes, and this you can do in the terminal, not in the R session, but in the terminal, especially in a Unix or Linux or Mac OS environment, or with the process manager in Windows. I don't know if this will work in Windows though, but you could. You will see that when you call MC apply, there are 5 processes of R running at the same time. One is the one responsible for administrating the overhead and everything, and then the other 4 processes are the ones being executed by MC apply. So these are actually distinctive processes, and you can see the process ID here. These are indeed different programs running in your computer, all handled by the MC apply code. Okay, so very, very robust way of doing things, of implementing parallel computing MCL apply. Okay. Quick summary of these functions. Any of the MC routines in parallel work particularly well when you have when you can make full use of processors on a single computer, and each task only reads from some big common data and distribute that. Things that you need to be careful with is when you modify the big common data structure, this can inquire in some memory blowups, but also in these race conditions that that may happen. This, as I say, I don't think works in Windows. Maybe in the latest version of Windows has been improving over the time, so maybe now it can run. I can tell for sure, to be honest with you. Maybe it's worth giving a try and monitor the process manager there. MC cores is not really a lie, but it's the number of tags and not cores. So on an 8-core machine, if you have multi-thread libraries, you can say MC core A, and then you will end with 64. So this is called hyper-threading. You don't need to worry about this tiny detail. It's something more to be aware of some subtleties. Okay, and if you have any questions about that, I will be happy to discuss this with you, but later maybe. Okay. Final part of the lecture, and I warn you guys, it will run a little bit over time today. Maybe not as I was expecting 15 minutes, but about at least 5 or 10 minutes. The last part I want to mention, and is this dichotomy we were mentioning since the beginning between compiled languages and interpreted languages. And now we recall this today, right? R is an interpreted language. But the nice thing of R is that it will allow you compile languages. So why you will do that? Well, because compiled languages, as we argue, are fast, and they are way faster than interpreted languages. So what could happen is, this is the usual way things go. You have a code, it's doing what you want. That's the first step. Have a code that does what you want and does it right. Then you say, okay, this code is too slow, or I got more data, or my data increases by a long factor, or a big factor, and then I say it's getting slower, so how can I improve that? Then you profile your code and see where that part is slow, and then you try to optimize that part, either using one of the parallel techniques that we discussed today, or you can offload that computation where it is slow to a compiled language. And that is what this last session is about. There are a couple of things. R comes with the ability of do what is called by compiling, and that sometimes helps, and I show you an example of this. But you can also write your own pure C++ or Fortran code interfacing with R, and we are going to see a few examples of this. The package to use is called RCPP for R C++, and this allows you to basically include C++ code within R. So we're going to see that. First thing I want to show you is what we call by compilation. And by compilation basically takes your functions and generates a compiled version of them. So what you need for that is the library compiler. We are going to use the library microbenchmark just to excuse me, just to measure things. And this enable sheet, which stands for enable just-in-time compiler, is to disable the by compilation by default. What happens nowadays is, because computers are getting faster and faster, relatively speaking, R by default tries to by compile anything. So as soon as we define a function, R will use it once, and after using once, will by compile it and remains by compile. So doing enable sheet 0 basically turn off that feature. Okay, so it's a trick just to show you how by compile actually improves your performance. So what I'm going to do is define a function that receives one argument n, and that's the same computations as we saw before. Repeats for that number of n a division plus an addition. So this is one expensive computation in terms of computer science, because there is a division involved, but it's nothing to be worried about. It's just a way to keep our wheels spinning. So the way to by compile a function is to use this compile fun command, cmp fun, of the function that we just defined. So lf will be our version, the live function version or the compile function, and then n is going to be something like 10,000. And now what we are going to do is we are going to micro benchmark both functions, the function that is not compiled, f, and the function that is compiled, using 10,000 times the computation inside. So what happened is, this is measured in milliseconds in this case. We call micro benchmark. We get a minimum, a mean, and a maximum. And what we can see by looking at each of the indicators, but in particular at the mean, is that the compiled version function is almost 10 times faster, right? We are talking about almost 18 milliseconds versus 2 milliseconds, 9 times faster if you wish. Okay, so it's a surprising fact that just by compiling you get this factor, and that is not so surprising if you think about R as an interpreted language and compiled interpretations being way faster. And that you can do with your own functions. Only thing you need to do is cmp fun, and boom, that's it. No major changes to your code whatsoever. Okay, so by compilation. It's not the same as actually compiling, but it helps. Okay. If you run a function multiple times, as I say, R will automatically bycompile it for you. Okay, so the reason for this bycompilation is that imagine that you have a library of functions and you call your function once. So the first time that the function is called is not bycompiled. And if this function is expensive in terms of time, then it's better that you just bycompile it. It will be ready for you to run. And so, you know, it's a way to optimize that flow of in the program. The enable sheet function is the one that allows you to turn on or off the automatic bycompilation, but by default is on, and I recommend you keep it like that. Okay. Now, real final part is RCPP. And so one thing is that RCPP has to be installed, and it's not one of the default packages in R, so it requires some manipulation. You can always do install packages, RCPP. The caveat here is if you're going to do this in a Windows machine, you need to also download RTools. Okay, and this is the link. So RTools is quite large and it will require some time to download, so it's probably not the best idea to do it during class, especially we are almost done. But you can try this at home, and I will invite you to do so because it's a really good performance improvement. Now, how we use this? There are two ways you can do that. As usual, library RCPP, because we have this function, this package, and we need to load it. And then we need to define functions, but the functions now will be defined as in C++ code. So in the very last slides, we're going to have a very fast crash course in C++. So this is a CPP function, C++ function, and you can see is a call, and it goes, whatever goes inside goes between quotation marks. It's going to be text. And this is the way that you define a function in C++. So this is the name of the function, times. Now remember, in C and in many compiled languages, the types of the arguments and the functions are not defined. So we need to explicitly say what is the type of the function. So in this case, int refers to an integer number. The function will return an integer number. That's what this is saying here. The function will receive two arguments, very similar to what we do in our functions, x and y. But again, we need to tell the compiler that these numbers are going to be integers as well. The function is going to compute an internal variable called product, which is the product of x times y, but it's also the type integer. As you can see, one of the main differences is that you need to put what type of variable it is everywhere. And then finally, return. And you can see there are some differences in the syntax, like the semicolon is mandatory in every line. That's a big difference. But other than that, the flow of the language looks pretty much the same. Define a function, arguments for the function, do whatever the function does, and then return. Now, if I do this, basically I'm defining a function called times in R, which I can use for 34 and 4 and get the result of 34 and 4. Okay, so that's the first approach. I can define now functions using C++, and these functions should be faster than using the counterpart in R. Okay, first idea. So I think I mentioned this first bullet point. The other thing is that these types, right? So many types, like integer here, is predefined in R. But some types in C++, they just don't exist. Now, RCPP has a nice interface to that. It can define integer vector, numeric vector, logical vector. All these types that are available in R, but usually not in C++ per se, are available in the R C++ family. So these are really interesting. Even has a function for NA. So compiled languages are really bad dealing with no data available, but RCPP is able to handle that. So that is a really plus sign on the RCPP side. Okay. So let's take a quick look at a snippet of code in C++. So this is like a script in R, but this in C or in C++. Main differences. This double slash are comments. So instead of using the hashtag as we use in R, we use comments. Okay, and so this is a comment saying this code is called my RCPP code. This include is like our library command, and you can see it starts with a hashtag. Okay, so hashtag include and then the name of the library between this greater and smaller than symbols. Okay, so this is like library, so it's loading the RCPP library. That's all what it's using. Then this username space RCPP is just to avoid writing RCPP everywhere. Okay, so it's a word to shortcut the commands that we're going to use. This is mandatory even when it is a comment / and double brackets. RCPP export is mandatory because this basically tells RCPP which is the function you want to export and make available in R. Okay, and this is nothing else than the function that we just described. The int times function receive x and y as integers. These are comments for the function as they should be, the product, and then the return. Curly braces, as in R, delimits the function, a call block. Okay? Now, this is a separate file. It's called myrcppcode.cpp file. In R, in our console, we will be loading library RCPP, and instead of using, as we were using before, the CPP function, we are going to use source CPP, which is basically like the source command in R. So this source command CPP will go and look for this file, bring this function and compile this function, and make it available for you. Okay? So any questions about this? So it's a very, as I told you, very crash course in C++ and how to use RCPP and C++ from within R. So the question is, why bothering learning C++, importing it from R, and so on? So this is the demo case, if you wish. Another example of a C++ code. So this is a lie to our announcement of the course. You are not only learning R in this course, you are learning C++. And you will see it's kind of true. After learning a particular coding languages, you are halfway through learning any other coding languages, because what matters is the way of thinking. So another example, my RCPP code 2. In this case, we saw this loading of the library from the CPP code. We saw the shortcut for not putting RCPP in front of everything, and this is the function we are going to export, RCPP export. In this case, the function, instead of returning an integer, is going to return a floating point number, a number with decimal points. That's why we use double. This is mysum. It's a function called mysum. It will receive a numeric vector x, so it's a vector of numbers, and a numeric vector y. Open curly braces, which defines my function. And this what will return is the sum of the product of these two vectors. Okay? Now, this is where C and other compiled languages gets tricky. We need to allocate memory for doing this computation. And the way to do that is to define n, which is the size. You can obtain the size similar to length of the vector x. And then initialize the answer with 0. So we need to put zeros in this variable answer, which is going to be what we are going to return at the end. And then there are not vectorized operations in C++, unlike in R, and we are going to use a for loop. So the for loop looks pretty much as the for loop we use in R, but again, we need to define the type of looping variable. In this case, I is going to be an integer that goes from 0 up to the value of the length of the vector n that we just defined here. And then we are going to increase the variable I by adding 1. So this is a shortcut in C++ to say I equal I plus 1. So I plus plus, and that's where the name of C++ comes from, is given by I equal I plus 1. And then this is another shortcut in C++. In answer, when you write plus equal, you say answer equal answer plus whatever is here. Okay? So this is a cumulative variable, as we have seen before, written as C++ if you wish. So what is happening is in answer we are accumulating x times y for each element in the vector, and then we are returning answer. Okay, I think I saw a question here. Richard, I have to. Okay, no problem, Richard. You can look at the at the recording later, but thank you. So that's what this function is doing. It's just computing the product between each of the elements in the vectors, adding them together and returning that. Okay, so that's my definition of this function. So we are going to source this call, and we're going to load the micro benchmark library for basically benchmarking these two functions. So x is going to be 1,000,000 random values, y is going to be another 1,000,000 random values, and then we're going to benchmark my sum given by the compiled version of this function. And the most optimized way we could do this in R. Notice that we are doing vectorization because we are multiplying the vectors and then adding them together. Okay, you can specify the units in this case as milliseconds for the report of micro benchmark, and that's exactly what I'm doing here. Okay, so we run that, units are milliseconds, and then my sum, the compiled version, you can see is almost 3 times faster than the best optimized way of doing this in R. And this is why sometimes you need to rely on compiled versions of your functions to optimize your code. In this case, we are talking about 1 second versus 3.5 seconds. Not much to sweat about, but you can imagine that this is a long computation. As I was saying, this can be the difference between running in a day or a month. Then you may want to go through this. Again, a tool that you can have available for working with if you need it. Okay. So you can do this also trying to do vectors. I'm going to skip this part and leave it to you to read just for the sake of the time. I don't want to extend way too much, but you can also use vectors as I showed you before. So you can do this numeric vector and try to optimize things doing that. Okay, so it's just another example. So my final comments for this lecture today. There is a lot of material and way more libraries related to high performance and parallel computing in R, especially they are put together by the CRAN task view on high performance computing and parallel computing. So it's a great resource to look at if you need to use things like CPU or optimization. That's a really good way to go. Just a few comments about today's lectures. Say your function profile until you know that the function works correctly. That's what I was saying before. Try to implement things correctly first, and then try to optimize if it is needed, right? If you are happy with the time, that's okay. Some of you were mentioning that in the last assignment, in assignment 4, the function was taking 2 minutes, and it feels like too long already. Maybe that is not necessarily a case for optimization, but maybe if it takes even longer, that's a case to consider. One of the first things you can try to do, very simple, by compilation. Okay, put your by compile functions in your utility files just by using cpfun. Don't be afraid of RCPP. Once you know a programming language, what matters is the way of thinking. You are more than halfway through of any other programming language, and CPP or C++ can be a little bit intimidating, but after you get used to this nomenclature and syntax, I promise you it will feel pretty much the same as programming in R, for instance. And if you need help, you know where to find us, where to find me. You can just write to courses on my email, and I will be happy to take a look and help you with any kind of troubleshooting that you may have optimizing your codes. Now, just a big summary, a quick summary of what we covered in the course. Most of the time we spend talking about programming and best practices in programming. We spend a good amount of time in modularity. I hammer you with concepts like functions and modular code, comments and documentation, all part of this best practices technique that we try to enforce in programming. And the truth to be told is that usually you spend more time developing this, but that will pay the price long way after you develop your code. It will help you to maintain very healthy and robust code. Useful techniques that we discuss in class, slicing, vectorization, and the apply functions, combined with the techniques that we discussed today, I think is a very good way to utilize R in an efficient manner. We saw a very quick glance of statistics and models and visualization and some nice tools I think are in visualization available for you to use. And today we discuss about how to improve the performance of your code with different tools and techniques. I also want to mention what we did not have enough time to cover in this course. Version control is a great tool in programming and in research, I would say. It's at the core of research reproducibility, of results reproducibility, and tracking changes. I will invite you to take a look at that. It's not complicated to use. It has some learning curve, of course, but it's worth spending the time learning. It gives you a confidence in your results and a way to reproduce results and keep track of changes that there is no arguing in having it. Another thing we didn't cover but is super useful, especially when you run your scripts in a supercomputer type of environment or a cluster type of environment, is running scripts from the command line and using command line arguments. Okay, we haven't discussed how to develop your own package. That can be course 2 in R if you wish. But after you have a mature set of scripts and libraries, you may want to publish your results and your packages in CRAM, make it then available for the community and for other colleagues of your same line of work. We haven't discussed much about the statistics. I told you we can have a whole course on statistics, about model diagnostics, hypothesis testing, applications of statistics, as you know. And we haven't discussed anything at all about machine learning, but it's a field that keeps growing very fast, and especially within the R community. Just my final comments. There are further opportunities for you to take signer courses and at the same time accumulate more credits toward your certificates if you're interested in that. For instance, we have a virtual summer training program that it will be starting in a few weeks. There is a variety of topics. You can look at it at this website, and I hope that we will have more courses available as the time comes by and we move forward in the year. Now, for my very final comment, I want to thank all of you for taking the course, especially in this particular format, in these unprecedented times where we cannot even meet in person, but we can meet through the lectures and online. So I really want to thank you for having taken the bet of taking this course online. I usually enjoy way more teaching it in person because I have the opportunity to chat with you, to meet you. But again, I want to thank you for taking the course, for sticking to the course. I know that I had asked you about a lot in the assignments, so I really want to thank you guys for sticking to the course and for all your questions during the lectures, in the chats, and in the office hours. And again, we will have office hours in the next coming weeks. So if you don't have any questions today, maybe on Monday, you may have some questions about what we covered today or the assignment. And I apologize again for taking my estimation was almost right. We are 13 minutes past the hour. So I'm going to finish here. But if you guys have any questions, as usually, we'll be happy to take them during in the chat in the next minutes or in the office hours.